In this lesson, we're going to introduce the concepts of redox chemistry and see how reductions and oxidations apply to organic chemistry. Let's start off with a quick overview of the types of reactions found in organic chemistry. There are only 6 fundamental types of organic reactions. First, we have rearrangements. A rearrangement is just a reaction in which atoms move within the molecule, creating new bonds and breaking old bonds. Essentially, it's the transformation of one constitutional isomer into a new constitutional isomer. So here you can see that these two molecules in this reaction have the same formula, but they are different structurally. The atoms are connected differently. That's a rearrangement. Next, we have substitutions. A substitution is simply when one atom or group of atoms is replaced by another. So here you can see that in the organic molecule, this bromine atom is going to be replaced by a fluorine atom. Then we have additions. An addition is when one molecule is literally added across the pi bond of an organic molecule. So if you look at this reaction, here we have an alkene reacting with HBr, and the entire HBr molecule was added across that pi bond. Eliminations are essentially the reverse of addition. An elimination is when a molecule is eliminated to form a new pi bond. So here we have this alkyl halide, and it forms a new pi bond. It forms an alkene, and as a result, another molecule, HBr, is formed. So it eliminated that HBr molecule to create a pi bond. The last two reaction types are reactions you've no doubt heard of before: oxidation and reduction. Now, you may have learned one or two mnemonics in some other chemistry courses that can help you to remember what oxidation and reduction are. First, there's Leo the lion goes grr, and that stands for loss of electrons is oxidation and gain of electrons is reduction. To me, that one's kind of wordy. I prefer oil rig, which stands for oxidation is loss of electrons and reduction is gain of electrons. When dealing with redox reactions on things like metals, the metal was literally gaining or losing an electron. Copper, for example. Copper can exist in 3 oxidation states: copper 0, copper 1, and copper 2. When copper is oxidized from copper 0 to copper 1, it literally lost an electron. When copper is reduced from copper 1 to copper 0, it literally gained an electron. Now, the covalently bonded atoms in an organic molecule don't lose and gain electrons, not in the literal sense. When a carbon or other covalently bonded atom is oxidized or reduced, it's not losing or gaining an electron, but it is gaining or losing electron density. So those mnemonics still work. You just have to add the word density after electron. So oxidation is a loss of electron density, and reduction is a gain in electron density. Now, the way that a covalently bonded atom gains or loses electron density is through manipulations of the number of bonds it has to electronegative atoms. An electronegative atom is going to pull electron density away from the atom it's bonded to. So an oxidation is an increase in the number of bonds to electronegative atoms. Oftentimes, oxidation results in a decrease in the number of bonds to hydrogen. And if either of these two things is happening, it's considered an oxidation. So if you look at this example, you can see that that middle carbon has 1 bond to oxygen, and it's going to a ketone, which has 2 bonds to oxygen. So that represents an increase in the number of bonds to an electronegative atom, so it's an oxidation. Note that that carbon also had 1 hydrogen on it in the reactant and 0 hydrogens in the product, so it's also an oxidation from that perspective. Conversely, a reduction would be a decrease in the number of bonds to an electronegative atom, or again, an increase in the number of bonds to hydrogen. Can be either or, often both. So if you look at this example, we have a ketone, and that central carbon has 2 bonds to the electronegative oxygen, and in the product, the alcohol has only 1. So it decreased the number of bonds to electronegative atoms. It's a reduction. The carbonyl carbon also has 0 bonds to hydrogen, and the product, that carbon has 1 bond to hydrogen. So it increased the number of bonds to hydrogen, and it's a reduction in that way as well. Covalently bonded atoms, like carbon, can have a variety of different redox levels. A redox level is nothing more than the number of bonds that atom has to electronegative atoms. A redox level is not really the same as a true oxidation state, although the terms are often kind of interchanged. Redox levels themselves are simpler than true oxidation states and generally more useful when learning fundamental redox reactions. So if we look at the possible redox levels for carbon, carbon can have up to four bonds, right? It has four valence orbitals, it can make four covalent bonds. And that means that there are actually five possible redox levels, because carbon can have as many as four bonds to electronegative atoms, but can have as few as zero. So here in this table, I have examples of organic compounds where we can see carbon in the five different redox levels. Carbon in the zero redox level is typically a carbon that's bonded to other carbons and hydrogens. In other words, it has no bonds to electronegative atoms. Things like alkane carbons. Carbon in the first oxidation state is going to have one bond to an electronegative element. So things like simple alkyl halides, where you have a carbon to halogen bond, and alcohols, where you have a carbon oxygen bond. Those would be carbon in the first redox level. Carbon in the second redox level is going to be when carbon has two bonds to electronegative atoms. And these are almost always aldehydes and ketones, where you actually have two bonds to the same electronegative oxygen. We see carbon in the third redox level in certain other carbonyl compounds like carboxylic acids and amides and nitriles. In each case, you can see that carbon is bonded three times to an electronegative atom. And then lastly, carbon in the fourth redox level are things like carbon dioxide, where we have a central carbon that is double bonded to two separate oxygens, giving it four bonds to electronegative oxygen, or other carbonyl compounds like this compound here, which is called urea. And you can see that it has four bonds, two to electronegative oxygen and two to electronegative nitrogen. So when it comes to looking at oxidations and reductions on covalently bonded atoms like carbon, rather than calculating true oxidation states, we simply look for changes in the redox level. An increase in redox level during a reaction is going to be an oxidation, and a decrease in the redox level during a reaction is going to be a reduction.